All right. So we're doing a graphing activity today. And it's been a minute since we've done a graphing activity. So I just want to review real quickly. When you're trying to scale out your graph, in order to get your graph so that it fills the whole space, what you want to do is count the boxes that you have. I'll help you out. There's 20. Then you're going to do your biggest value minus your smallest value and divide that by the number of boxes. You're going to make the corner of the graph your smallest value from the data table. And then for each box, you're going to add the number that you got from 2. So we're going to do this first graph together, and then the rest of the graphs you're going to be doing on your own. Okay? And we're going to save these steps. All right, so this first one, we're looking at the elemental property atomic radius, which of course is the distance from the nucleus to the outside energy shell. All right, and so basically it's the size of our atom. How big is our atom? And we're going to look at period 3 and group 2 data. So we're going across a row with one graph, and then we're going down the group with the other graph. So they asked us to graph the atomic number on the x-axis and the atomic radius on the y-axis. So let's go ahead and label those real quick. We're going to do atomic number down here, and we're going to do atomic radius over here. Okay. Once you have plotted your points, use a ruler to connect each dot to the next dot. All right, so let's start with atomic number. This is pretty straightforward. We know that there are 20 boxes on the graph, and I will tell you that's consistent all the way through this worksheet, so you don't actually have to count the 20 boxes. There's 20 boxes every time. All right, so we're going to take our biggest number minus our smallest number and then divide that by 20. So I'm going to do 18, because that's my biggest atomic number, minus 11. That gets me 7. Sorry, I know there's a glare. That's terrible. Then I'm going to divide that by 20, and that gets me 0.35. Now, if I look at my boxes, each box is 0.35, but if I try to label every single box, this is going to get really smooshy. It's pretty small. I'm actually going to multiply this number by 3. This is the number I need for each box, but if I multiply it by 3, that allows me to just label every third box. So I'm going to do that times 3, and it's 1.05. I'm going to go ahead and just round that to 1. Okay? That's going to leave us a little off the graph at the end, but it won't matter. All right, where we would normally have 0, we're actually going to label that our smallest number, which in this case is 11. We're going to skip 3 boxes, add 1. Skip 3 boxes, add 1. Skip 3 boxes. 1, 2, 3. There we go. Add 1. Make sure you put the little hash on there so that you can see where your lines are. Now you'll notice we needed to go up to 18, and we're short a box. So I'm going to do 1, 2, 3, and I'm going to put 18 just a little bit off the grid. That's all right. It's better than having it smished, because if we did every other box, it just gets real smishy. All right, so now let's do the same thing for our y-axis with our atomic radius values. You'll notice that our biggest value is on the top this time, and our smallest value is on the bottom. So we're going to do biggest minus smallest, so that's going to be 19.1 minus 9.5. That gets me 9.6. I'm going to divide that by my 20 boxes. So each of my boxes is 0.48. Let's call that 0.5. I'm going to multiply that by 3 so I can skip every third box. Let's call it 1.5. So I'm going to put my smallest number, 9.5, where 0 would normally be. And then we're just going to take that 9.5 and I'm going to add 1.5 and skip 3 boxes. So skip 3 boxes, and this is 11. Add 1.5, skip 3 boxes. This is 12.5. Add 1.5, skip 3 boxes. This is 14. Add 1.5, skip 3 boxes. This is 15.5. Add 1.5, skip 3 boxes. This is 17. Add 1.5, skip 3 boxes. This is 18.5. Add 1.5, skip 3 boxes. And again, we're a little off the grid because we rounded, but that is okay. So then once we've got our x and our y axis, we want to plot our points on the graph. I'm going to check them off as I plot them just so that I don't get lost and accidentally double plot something. I would also suggest using a ruler so that you can stay on the correct line. All right? And then we want our plotted points to be very visible when we're done. So we're going to put a dot and then circle it. You could also use an X. That's acceptable too, because at the end we're going to connect each dot with a line. And so we don't want our dots to get lost in the line. All right, so our first is atomic number 11, which is right here along the y-axis, and then atomic radius 19.1. That's going to be right about here. I'm going to put a dot and I'm going to circle it. All right, my next atomic number is 12. So I'm going to line up my ruler along the 12 line, and then let's mark that one off so we know we did it. Then we have 16.0, which is going to be right about here. So make your dot and circle it. All right, our next X value is 13. And our Y value is also 13. All right, our next atomic radius is 14, so we're going to line my ruler up. And then we have 11.8 as our y-axis. It's going to be right about there. Then we have 15, so I'm going to line my ruler up at 15. And then 11.0 is nice, easy, right on the line. Atomic radius 16. And then 10.2 is going to be just north of here. 17. Be right about there. And then 18 is right on the x-axis, 9.5. Okay, so as we go across a row of the periodic table, notice that our atomic radius is decreasing, which based on what we learned in the periodic trends foldable, that's what we would expect. Okay, so we went from 11 to 18, so we're looking at row 3 of the periodic table. We're going across here. And as we go across, our atomic radius goes down. So we're going to take our ruler and we're going to draw this nice and neat. Beautiful little curve we got going on there. So this is an inverse relationship. As the atomic number increases in a row, the atomic radius decreases. Makes good sense. So let's look at these questions, because what you need to be able to do for your aerial project is this third question down here, the CER using Coulomb's law. Remember, we're going to use our acronym ARIEL, attraction, repulsion, divided by the energy levels. All right, so as you move across a period of the periodic table, what is happening in the following parts of the atom? Total number of protons. Well, as we go across a row, remember our protons are determined by the atomic number. So as we go across the row, the atomic number is increasing, therefore our protons are increasing. So it increases. The same is going to be true for our electrons. Remember, the atomic number is protons, but in an atom, our protons are equal to our electrons. So that should be increasing as well. Oops. Now, number of energy levels. Remember that each row of the periodic table is an energy level. So if we're staying in the same row, we are not changing our energy level. This is all third energy level that we're working in. So our number of energy levels is going to stay the same. Okay? Based on your graph above, as you move across a row of the periodic table, what is happening to the atomic radius? Well, we can see very clearly from our graph that our atomic radius is going down. Okay, so it is going to decrease. Now here's the tricky part. This is what you have to have on your aerial project. So we're going to practice a whole bunch of these with different graphs. Use your answers to question 1 to explain why the trend in question 2 exists. Make sure to include ideas of Coulomb's law or Arial. I'm actually going to do this on a sticky because there's not a ton of room on there, and I don't want to write it so small you can't read it. Okay? So remember that Arial stands for attraction, repulsion, and energy levels. And let's be more specific. Where does attraction come from? This is going to come from the nucleus, and it's based on the positive protons in the nucleus. Okay? Our repulsion is coming from lots and lots of electrons. Okay? The more electrons we add, the more repulsion we're adding to counterbalance our nuclear charge of attraction. Okay? And then our energy levels. Energy levels are basically going to help us figure out how far we are from the nucleus. And remember that the further away we are, the less attraction you're going to feel. So energy levels really matter when it comes to how attracted are our outer electrons to our nucleus. Because the more energy levels we add, the further and further away from the nucleus those electrons are getting. So to answer this question, we would say something to the effect of, as you go across a period, the atomic radius decreases. Across a row, protons are added to the nucleus, increasing the attraction to the electrons. Because we are not adding energy levels, the electrons remain the same distance from the nucleus. As protons are added, and attraction increases, these outer electrons are pulled closer in, decreasing the size of the atom. Sorry, that went a little off the page. There we go. Now, the only thing that I don't love about this is where I said the electrons remain the same distance. What we might say there instead is the electrons are not getting further away from the nucleus. That might be more correct, because as we add protons, they're actually getting closer to the nucleus. So we might actually add there that the electrons are not getting farther from the nucleus. That might be more correct to add. But the most important part here is to talk about, here's the trend that we saw, how is the structure of the atom changing, and then there's my attraction, there's my energy levels. There's not a significant amount of repulsion that matters in this one, so I've left that one out. But we've talked about attraction, we talked about energy levels, we talked about distance from the nucleus, we talked about attraction increasing, and then related it to the decrease in the size of the atom. So that is a very complete answer to this question. And this is what the kind of answer that I'm looking for on your aerial project. Okay, so I'm going to leave you the rest of these graphs to do on your own. Okay, so you're going to do one. This one is also atomic radius, but this time instead of going across a row, you're going down a group. If you look at it, this is group 2 of the periodic table. You're going straight from beryllium down to radium, excuse me. You're going to graph it exactly the way we graphed this. So make sure that you do your steps to scale it. Okay. And then you're going to answer the exact same set of questions, but your answers will be different. So the questions on all of these graphs are the same. It's your answer that's going to change based on what you see in the graph. Okay, so you're going to do atomic radius down a group. Then you're going to look at ionization energy, the ability to remove an electron. You're going to do that same row of the periodic table with a different property. And then you're going to do the same group with a different property. And again, questions stayed the same. What's changing is your answer based on the graph. And then the last property you're going to look at is electronegativity. Okay? You're going to graph that same row. You'll notice that with electronegativity, our noble gas does not have a value because it does not jump into compounds. So there is no electronegativity value for the noble gas of the row. Okay? So you'll graph that, same questions, and then the same group just with electronegativity. So you've got a number of these graphs to do. Now, very important, since I did this graph with you, this one you cannot use for your aerial project. All right? Can't use this one because I did that with you. You may use any of the other graphs that you're going to do on your own. You may use any of those for your aerial project. All right? Happy graphing.